Hi, so in the previous lectures, we discussed about the process of obtaining approximate solution from the governing partial differential equation. Okay, we have seen that this process involves two steps. The first step is discretization, which means the conversion of governing partial differential equation into a system of linear algebraic equation, and the second step is the solution of this system of linear algebraic equation to get the approximate solution. Okay, so let us denote this approximate solution to be u of x comma t. Okay, but there are some very important questions that are yet to be answered. Okay, so the first one is that what guarantees what is the guarantee that the approximate solution will be close to the exact solution? Okay, the approximate solution is close to the exact solution. Okay, so what we are trying to say is the governing partial differential equation we considered earlier is dou u by dou t minus alpha dou square u by dou x square equal to 0. This is the partial differential equation. Let's say the exact solution to this is the exact solution is u tilde of x comma t. Okay, and the discretized equation using explicit scheme, let's say what we have got is u at node I at time level n plus 1 is 1 minus 2s times ui n plus ui plus 1n plus ui minus 1. Okay, so solution of this the resulting system of linear algebraic equation obtained from the discretized equation will give us approximate solution. Okay, let's say that is u of x comma t. Okay, exact solution is u tilde, approximate solution is u. So how do we ensure that the approximate solution represents well the exact solution of the governing partial differential equation? Okay, this is a very important question because if we cannot ensure that the approximate solution represents the actual exact solution, then there is no point in doing everything that we are doing. Okay, if the end result is not a close approximation to the exact solution, then what is the point of doing this? Okay, so this question cannot be directly answered. A related question that is important is that under what conditions the approximate solution, so u of x comma t, is close to the exact solution, which is u tilde of x comma t. Okay, so let's say we cannot guarantee from the first question, let's say that we cannot guarantee that the approximate solution will be close to exact solution, but there are under certain conditions that they do so. Okay, so we want to know under what conditions this happens. Okay, so this question introduces the concept of convergence. Okay, so now if we go back to this graph again, the governing partial differential equation has an exact solution. Okay, by convergence we mean as the mesh spacing and the time step, if they both go to 0, we mean that the approximate solution represent exact solution. Okay, so by convergence we mean as the mesh spacing and the time step goes to 0, then the approximate solution from the computational scheme approaches the exact solution. Okay, this is what we mean by convergence. When we say the solution is converged, this is the meaning of this. Okay, so the error, in other words, the error E of x comma t, which is u exact minus the approximate solution, tends to 0 as delta x and delta t approaches 0. Okay, but convergence is very difficult to establish. So convergence is our interest. Okay, we want to study convergence of the numerical scheme, but convergence is very difficult to establish. So we cannot study convergence of a numerical scheme directly. So what we are going to follow is we are going to follow an indirect approach. An indirect approach to study convergence. Okay, so that brings in this very important theorem, which is Lax equivalence theorem. Okay, so this indirect approach is the base of the indirect approach to study convergence is the Lax equivalence theorem. Okay, so Lax equivalence theorem says that so given a well-posed linear initial value problem, and a finite difference approximation to it, okay, that satisfies consistency condition, then stability, okay, then stability is the necessary and sufficient condition for convergence. Okay, in short, this says that consistency plus stability gives convergence. Okay, we have not yet discussed about convergence, the consistency or stability. Okay, we have discussed convergence. That means as the mesh spacing tends to 0, the approximate solution approaches the exact solution of the partial differential equation. But we have not yet discussed about consistency and stability, which we are going to do now. Okay, so let us look at this theorem once again. So given a well-posed problem, okay, we know what a well-posed problem is. Okay, the solution exists, solution is unique, and the solution varies continuously with auxiliary conditions. Okay, this we have briefly discussed in the beginning. Okay, so for a well-posed linear initial value problem and a finite difference approximation to it, so the classical statement of Lax equivalence theorem talks about finite difference, but it is applicable for finite volume and finite element also. Okay, it is not restricted to finite difference and finite volume. Then if the scheme is consistent and stable, then it will converge. That is the main statement of Lax equivalence theorem. Okay, so this theorem is of great importance because it is relatively easy to prove consistency and stability than theoretically addressing the convergence. So it is easy to prove stability and consistency of numerical scheme than directly addressing convergence. So this is the indirect approach we are trying to say. Instead of directly applying convergence, we are going to study consistency and stability separately. Okay, but this theorem is strictly applicable only for restricted class of problems, which is linear initial value problem. So that is the restricted class of problems for which this theorem is applicable. Okay, for linear initial value problem, so Lax equivalence theorem is necessary and sufficient condition. Okay, but all real problems are non-linear. I mean, most of the real problems that we want to solve, be it a fluid mechanics problem, heat transfer problem, or structural dynamics problem, they are non-linear. So real problems are non-linear and they are mixed initial boundary value problem. Okay, so for these cases, Lax equivalence theorem provides only the necessary condition but not sufficient one. Okay, so the reason why this theorem is very important, because even for practical non-linear initial boundary value problems, this condition should be satisfied if we want to get a convergence scheme. Okay, this theorem, if this is not satisfied, then we will not get convergence, but if this is satisfied, then we cannot take convergence for granted for non-linear initial boundary value problems. Okay, in any case, it provides the necessary condition. It has to be satisfied. Okay, so now let us look at these ingredients of convergence: consistency and stability separately. Okay, so let us start with consistency. Okay, what do we mean by consistency of a numerical scheme? Okay, so discretization gives rise to, so when we say, okay, I am drawing this curve again and again because it's very, very important. Okay, so when we say discretization, I am repeating from the earlier class, we are not talking about mesh generation. When we say discretization, we mean converting the governing partial differential equation into a system of linear algebraic equations. Okay, so this is what we mean by discretization. Okay, by consistency we mean as delta t and delta x tends to 0, then the system of linear algebraic equation should be equivalent to the original PDE. This condition is the consistency condition. Okay, so we use discretization to go from left to right. By consistency condition, we mean if we put the time step and the mesh spacing to 0, then the original linear algebraic equation should exactly represent the original partial differential equation. Okay, so this for a finite difference approximation, for finite difference approximation, consistency mean truncation error goes to 0 as the mesh spacing and the time step go to 0 for a finite difference approximation. Okay, so let us consider the explicit scheme for the unsteady diffusion problem or unsteady heat conduction problem, which we have discussed in the last video. Okay, so the governing equation is dou u by dou t minus alpha dou square u by dou x square is 0. This is the governing partial differential equation. Okay, so while doing the finite difference approximation, so for doing finite difference approximation, so we write ui n plus 1 using Taylor series. We can write ui n plus del t dou u by dou t plus del t square by 2 dou square u by dou x square at I and n. Okay, the derivatives at node I and at time level j. Okay, so from here we can write dou u by dou t to be u I n plus 1 minus u I n by del t minus del t by 2 at I, okay, plus it's an infinite series. So let's say this is equation 2. Okay, so similarly we can write the spatial derivative, second order spatial derivative to be, which we have done already in the previous lectures, to u I n by delta x square, okay, plus del x square by 12 dou x to the power 4 n I, okay, this is, let's say this is equation 3. Okay, now substitute equation 2 and 3 here. Okay, so substitute equation 2 and 3 in 1. Okay, so we get instead of dou u by dou t, we have u I n plus 1 minus u I n by del t I n plus infinite terms, okay, plus alpha times alpha power 4 and all the terms that we left out equals 0. Okay, so rearranging this we get square equals to del t by 2 plus the left out terms. Okay, so the left hand side is actually the discretized equation, okay, and the right hand side is the truncation error. Okay, so when we apply finite difference equation, we are not actually solving the original equation, instead we are solving the modified equation. So while using finite difference approximation, we are actually solving a modified equation. Which is dou minus alpha dou square u by dou x square minus e t. This is the, let's say the truncation error DET equals to 0. This is the equation that we are solving instead of the original partial differential equation. Okay, so for the scheme to be consistent, this truncation error should go to 0 as delta t and delta x tends to 0. Okay, so this is the case for the explicit scheme that we are considering. As you can see, that the truncation error goes to 0 if both delta t and delta x goes to 0. Okay, so this explicit scheme is stable, and we can also show that the implicit scheme is also not stable, also consistent, which means that by delta t and delta x tends to 0 we will get back to the original governing differential equation. Okay, so, but by now you might have an impression that since we are using Taylor series based method, consistent can be taken for granted. Okay, that is not true. Okay, so consistency cannot be taken for granted. Okay, we will see one example now. Okay, so we are going to consider something called Dufour-Frankel scheme. Okay, so instead of using forward difference approximation, we use central difference approximation for the time derivative. Yes, alpha n by del x square equals 0. Okay, so this seems to be by a very logical approximation, because the truncation error of this one is order of delta x square, the truncation error of this one is order of delta t square. So both have a second order truncation error. Okay, this seems to be a logically correct one to do, and this is called Richardson scheme. Okay, the problem here is that this is unconditionally unstable, which we are going to see in the next lecture. Okay, which means that even for delta t tends to 0, we will not get correct solution. Even when delta t tends to 0, no physically correct solution will be able to find using this Richardson scheme. Okay, and this can be rectified by using the following approximation. So we approximate uin to be uin plus 1 plus uin minus 1 by 2. Okay, so instead of this term appearing here, uin, we are going to use this approximation. Okay, so the resulting scheme would be 2 delta t minus alpha times it will be uin plus 1 plus uin minus 1 plus ui minus 1n by del x square. Okay, and plus the truncation error would be 0. If we consider the modified equation, this is what we get. So the truncation error looks something like this. Okay, so truncation error looks like alpha del t by del x to the whole square and dou square u by dou x plus order of delta t square delta x square. Okay, this you do it on your own. Okay, this is for you. Derive truncation error for Dufour-Frankel scheme. Okay, derive this. Okay, as you can see from the truncation error, for consistency, delta t by delta x tends to 0. Okay, which means that the value of time step should be much smaller than the grid spacing for consistency. Okay, so this is not a consistent scheme. Okay, so this is not a consistent computational scheme. Okay, so the point here is that since we are using Taylor series based approximation, it doesn't mean that we can take consistency for granted. Okay, so let me briefly review what we have discussed here. We started talking about convergence. By convergence we mean as delta t and delta x tends to 0, the approximate solution of the system of linear algebraic equation approaches the exact solution of the original governing equation. Okay, that is convergence. This is our interest. Okay, so convergence is our interest, but it is very difficult to study theoretically. Okay, and Lax-Ventrop's theorem came to our rescue, that provide us a possibility to study convergence by indirect means. Okay, their convergence, it implies consistency and stability of the scheme lead to convergence. Okay, this is what Lax-Ventrop's scheme says. That we studied convergence in this lecture. We will discuss about stability in the next one. Okay, I'll stop here. Thank you.